Good morning, students, and today we'll be looking at a very interesting topic called pruning, which is one of the method that deals with how do we actually reduce the size of the model. Hence, we can run the same performance with the models being smaller, right? So, yep, and that technique is called pruning. Before I begin, this tutorial is based on another tutorials called torch ticks plus padded plus bidirectional LSTM, which is under the classification folder, right? So it's right here. The reason why I told you is because here in this tutorial, I will be using models called LSTM.pt that is actually created inside this classification tutorial, right? Simply because I don't want to train again, but I just want to demonstrate the pruning process, right? But anyway, that is that. And most of the code is already coded because they are all based on that LSTM tutorial. And the main part is simply mostly about pruning, right? So let us run this code block by block, cell by cell, and then we can go to the business right away, right? Great. So firstly, I have do the basic things, set the torch device and the manual seed. And here's my version and my torch text version. And here I'm loading some news classification data sets. And here I'm setting up the training and validation, and I'm also deleting some of the data set that is too much so that we can train faster and do everything faster. Second, we do some pre-processing. So we are done with loading data set. So second, we are doing some pre-processing. So here I'm loading some tokenizers from SpaCy. Next, I numericalize the tokens in which I set the Ankh padding, beginning of sentence and ending of sentence as the first 4 tokens I have. So they will be assigning ID of 0, 1, 2, 3, right? And then the other tokens will be 4, 5, 6, and so on. Here I will be also loading fast text embeddings, which is similar to WordDirect and Glove. But here I'm just gonna load the embedding so that my LSTM can work very well right at the beginning. So right here, I'm just saying that for all the vocabs I have, please get the vectors by tokens. And I can also check the shape, which is basically I have 52 vocabs. Each of them, the size of the vectors are 300. Right here, I'm preparing, so I'm done with the embeddings and also I think the pre-processing. So let me just close them down to make them very clean. And then I'm preparing the data loaders in which the text pipeline is simply tokenizing and then numericalizing for the label pipeline because data set gives me 1, 2, 3, 4. So I turn them into 0, 1, 2, 3, right? Because PyTorch expect to be this 0, 1, 2, 3. Here I'm just gonna write a function called collate batch, which will be used in the data loaders, in which I simply apply the label to the label pipeline and then append to a label list. Put the text into the text pipeline, turn them into tensors, and then put them into a text list, and then put the length into the length list. So you can see that the collate batch, the only function it has is just put everything into chunks, simply because PyTorch expect a chunk of labels, a chunk of text, instead in the zip form, right? They want them into chunks, right? Notice that we have this path sequence to make sure that all the sentence in the batch is of equal length. And right here, I have my data loaders in which I call my collate batch function in the collate function. And then finally, I have my LSTM model in which I simply put the text into the embedding. I pack the sequence and then send them to the LSTM. And finally, I get the forward and the backward hidden states, concatenate them together, and send them to the FC layers. And here are the setup of the LSTM in which I set the embedding to be my fast embedding. And here's the cross entropy loss, the accuracy, and the function for evaluation, and the test loader length, which is needed when we call the evaluate function. And because I already trained, this tutorial is not really to demonstrate how we train, but mainly to get the initial model and try to see that without pruning, this is the accuracy, right? So now I'm just gonna load the model and check the accuracy. And if I'm not wrong, it's around 90% accuracy. If this goes too long, I can pause my video, but let's see. Okay, great. So our test accuracy is 91%. So our purpose now is to check whether after pruning, this accuracy is gonna drop. So let me just close this down. And also this one. So now we can do the pruning, right? So in pruning, actually you can do it from scratch by yourself, simply prune the weights. But PyTorch also provide a very nice utilities called torch.nn.utils.prune. So let us inspect a layer. And in this FC layers, we have 512 in features and out features is 4. So if we calculate, this should be roughly around 2,448 parameters. So we can also apply this list. Sorry. And then we can also print each of them, and that you can see that the weight, the shape is 4 by 512. So you can, this is basically equal to okay, wait a minute. So this is basically equal to 2,448 parameters, and the bias is only 2,448 parameters. Before I move on, I have to mention that in PyTorch, there's also a parameter called name buffers. And usually this guy hold a lot of hidden variables, in which I just want to show you because the pruning we will later on create something called weight mass will be put in this buffers. So let us try to randomly prune here. So here I'm just gonna randomly prune like 0.05. So let me just change this to 5%. Right? It's called random.unstructured. And what I'm gonna do is put it into this FC layer. And once I do that, you can list the FC name parameters, and you can see that now the weight parameter is gone, and now we are replaced with something called weight original, right? And if you check a look at these parameters, they are still the same. They are still the original weight. And now you may wonder like, okay, so where does the pruning happens? And if you take a look at this name buffers, you can see that there's something called weight mass, and a lot of 0 is applied. So what does this do is that during the forward pass, this mass will be multiplied with this weight original, resulting in the weight prune, right? So you can imagine that this 0 will be up multiplied with this minus 0.1492, and resulting into this numbers being gone, right? So this is the way PyTorch does things. How do we know that what are the result, the final weight looks like, right? So you can actually do fc.weight, and this is the weight that looks like, right? And this one is actually the one that is not being pruned. And if I'm not wrong, is this? Hopefully I'm right. Okay, that's correct, right? One more thing I want to make sure that you know is that this is something internal. So if you do fc._forward prehooks, you can see that there's actually prehooks implemented in the forward pass. So this hook will be applied every time you do a forward pass, before forward pass, right? And what it does is that it's gonna multiply this mass with the weight original, resulting into this weight, right? So this is just to make sure that for those who are wondering, like, okay, do we really have this hook? You can call this attribute to make sure that you know that actually everything is pruned correctly. Now let us try to test the accuracy of our model after pruning. Hopefully this does not take too long. Okay, great. So it seems like once we pruned 5%, we still able to retain 88% of accuracy, which is quite nice, right? If we want to make everything permanent, right, we just simply remove the weight parameters from FC. Now you can see that we got that the weight parameters is now the pruned version, right? So this is basically the permanent version. Then, but anyway, random pruning is not so nice because you just randomly prune without understanding which parameter is actually important. We can actually learn something. By the way, let me just close this down to make this nice. So because, okay, give me 1 second. Maybe I can, I'm not sure. Okay, somehow I cannot close this. Maybe, okay, great. What we're going to introduce is something called magnitude pruning. So it can mostly prune based on the lowest magnitude, not randomly prune. Because we believe that the weight that has a very low magnitude usually are the one that is not so important, right? So when we say magnitude, is not like negative numbers, it has the lowest magnitude. I mean absolute, right? When you absolute the weight, any numbers that is close to 0 is mostly has very low importance, right? Those will be pruned. So before anything, how about I reset my model and I simply load the model again. And what I can do is something called L1 underscore unstructured instead of random unstructured. And here maybe I can do 0.95, right? And here is the nil weight that is being pruned. And now I can apply my pruning and see how does it perform. Okay, great. So it seems like you can see that magnitude pruning is much better. Even though we lost 5%, we still can retain 91% of accuracy, right? So make sure that you use magnitude pruning whenever it's needed. Now, so let us close this. You can also do something called, you can prune multiple parameters in a model using this for loop. So you just simply loop all the modules, right? And if that module is embedding, you can do L1 unstructure. And if this is a linear layer, you can do another L1 unstructure. And you can always prune in different sparsity, right? And you can also print the name buffers to make sure that everything is pruned nicely. So you can see that there's an embedding weight mass and FC weight mass. Here I'm actually pruning a lot of linear layers, right? So I'm not sure this is gonna go well. but let us try to see this. And you can see that a huge amount of loss is reduced because we have pruned a lot of parameters. You can also do global pruning, in which you can prune everything in the whole. So you can set that these are all the parameters you can prune, and you want to say that you want to prune 0.7, right? So you're gonna reduce all of them in an equal fashion, in which the total parameters to prune is reduced to 0.7, right? And what you want is L1 unstructured the same. So this is called global pruning. And now you can actually print what are the sparsity left. You can see that. So the embedding is left with 69. Our STM weight is left with that. FC.weight is left with that. And then you can see that finally the whole model is left with 70%. And now let us try. And because we prune like globally with L1 unstructured, we equally distribute what are the weight that can be reduced, right? So there will be a lot of weights that is like not so important in each of these layers. So when we prune like this, we are able to still gain quite a good amount of accuracy, right? Because we equally distribute them. So most of the bad weights can be pruned anyway, right? Right. Great. So those are the tutorials, and definitely let me close this first. Sorry. Lastly, if you want to create your own pruning, what you have to do is simply extend the base pruning method. And in what you have to create a function called compute mask, get the default mask, and then you want to do whatever you want to with this mask, and then return that mask, right? And then finally, you can apply this method to whatever module you want to do, right? So those will be the idea of if you want to create your customized function. One thing I want to say is that if you do what I told you in this tutorial, you are able to prune. That is correct, right? But you can see that my tutorial is simply setting the parameters to 0, right? So it does not really delete the parameter itself. So because of that, it will simply make the network with more zeros. Thus, there's less computation necessary, but at the same time, it does not actually improve the inference speed because you still have those parameters. So one way you can do is simply delete the layers. So for example, if I have so what you can do is, for example, if I have this layer called here we cannot delete any layers, too much layers, but in the transformer, for example, you have some heads, right? If you can just delete the heads, the whole heads, then you can improve the inference speed. Or you can delete the whole feed forward layer, you can improve the inference speed because you are not simply setting the numbers to 0, right? So yep, that I call structure pruning. But anyway, those for the pruning is a very powerful technique. So make sure you use it well. Thank you very much and see you next time. Bye-bye.